So here we can see water composed of one atom of oxygen, two atoms of hydrogen, and of course water is a compound, whereas previously all of these examples here are single elements. Here's our first compound, H2O, water. Carbon dioxide, CO2, there's one atom of carbon, two atoms of oxygen to form the compound carbon dioxide. CO2 is also a molecule, water is too. Sulfur is a molecule because there's two more atoms there. Phosphorus, P4 is a molecule. O2 is a molecule. H2 is a molecule. So these are all molecules. Here there are only three compounds. Again, a compound is something that has two or more different elements stuck together. And so here we have two elements, hydrogen and oxygen, stuck together to make water. Here we have carbon dioxide, CO2, carbon and oxygen stuck together. Here is a molecule of glucose, C6H12O6. And so here we can see 6 carbon atoms, 6 oxygen atoms in red, and then 12 hydrogen atoms in white. So when we talked about electrolysis of water earlier, this is sort of an apparatus that will do that. Here we can see we initially have water, and what you're having to do is provide a current. The current is referred to as electrolysis. You're providing energy into the system because water is not going to break down into hydrogen and oxygen gas naturally. You have to have some sort of energy source in order to break it down because the reaction is a non-spontaneous reaction, so you have to input energy, and so you're able to break down this compound into the single elements, hydrogen gas and oxygen gas. Here's another picture. They're showing a fuel cell and how it generates electricity by using hydrogen and oxygen, combining them together to produce water. And so because these are higher energy reactants here, the products are going to be lower energy, but you're harnessing that energy and you're able to create power from it. Here's a picture of your cell phone, and it's showing you all the different types of elements that are used to create your cell phone, including gold. And you've probably heard of some people collecting old cell phones and trying to harvest the gold out of them. And if you get enough cell phones together, you end up you're able to actually recycle a lot of different metals that are precious metals or very expensive metals. Copper is expensive, and so you can do that. But anyways, just showing you the different types of elements that are used in your cell phone to make your cell phone. So next we need to talk about physical and chemical properties. It's really important to understand the difference between these two concepts of a chemical change versus a physical change. So if you are talking about a substance, every substance you talk about, you can write out a list of physical properties. Okay, you can even do this with people if you wanted to. List out maybe a little bit about their personality and how it's a little bit different from someone else's. Well, a substance will also have, carbon for example, is going to have certain physical properties. Okay, so examples of physical properties of carbon. It's going to have a certain density. It's going to have a certain color. Carbon is usually black, depending on your source of carbon that you're looking at. It has a certain hardness. It has certain melting and boiling points, electrical conductivity, and other things that you can look up about the element. Okay, so that's referred to as a physical property. Okay, so all substances have physical properties. And so physical change is if the substance doesn't really change chemically, but it changes in terms of the states or the properties of matter without any chemical change occurring at all. So you've observed chemical or physical changes before. We see them all the time. One example is melting butter in a pot. And so the butter initially was a solid, and now you can still see part of it as it is still, part of it is still a solid. But most of it has converted into the liquid form. Okay, and so is it still butter? Yes, it is. It hasn't changed chemically. Okay, tastes the same for the most part, but it is still butter, but it has undergone a physical change. Here we see another pot on the stove, and you see steam condensing inside a pot. This is also a physical change. So obviously this is a pot that's on the stove and it's hot, and you have water that is becoming a gas and going out of the liquid phase into the gaseous phase, and then it hits the cool surface of the top of this lid here, and then it condenses down back to a liquid. And so that, again, that's also a physical change. So here we're talking about physical changes being just changing the states of matter, going from a solid to a liquid, or going from a gas to a liquid. And so any kind of phase change is considered a physical change. And so what about chemical properties? What is a chemical property? So anytime matter is converted into another type, okay, it's a chemical property. So for example, when we're talking about water being converted to hydrogen, oxygen, gas, and that's a chemical change. So it would be a chemical change because the matter is changed into another type. It's no longer a water molecule, it's hydrogen and oxygen gas molecule. So that's referred to as a chemical change. So what is a chemical property? Chemical property examples are flammability. If something's able to catch on fire and explode, possibly, that is a chemical property. Toxicity, acidity, reactivity, heat of combustion. So a lot of things we're going to talk about in this class. Some of those will be chemical properties of substances. A lot of times you will find chemical property information on Material Safety Data Sheet, or MSDS. And that information is given to you because you have to know if a substance is toxic, if you're working with that substance, if it's flammable, etc. So here is an example of differences in chemical properties. Here we have iron, and we can see that some of the iron has rusted to form iron oxide. Okay. So iron, the property of iron is it can rust. That is a chemical property of iron. Chromium does not rust. Stainless steel does not rust. Okay, those are properties of different elements or compounds. So chromium does not rust, and so here's a motorcycle that has a lot of chrome on the surface of the metal there in order to prevent it from rusting. And so these are all chemical properties. What about chemical changes? So one of the, I think it's like the third lab that we do this semester is the reaction with copper lab. Maybe it's the fourth one. But anyways, we end up creating this brown nitrogen dioxide gas from reacting nitric acid with copper. And so it's kind of neat to see a color gas because it's something you may have never seen before. And so that's an example of a chemical change. Burning a match is an example of a chemical change. Cooking meat on the stove. Okay, these are irreversible processes. You can't uncook meat. You can't unburn a match. Once you have a chemical reaction that occurs, it's converted your reactants to products, and so you can't go, well, technically you can go back, but for, let's not think about this too much, but technically, let's just say it's a reversible process, but you can't do it very easily, okay? I mean, with burning a match, you can't really reverse that, all right? What about bananas becoming overly ripe? Unfortunately, wouldn't it be cool to be able to reverse this process? But you can't. It's a chemical change that's occurring. Okay, the banana's giving off gases, and basically the banana is becoming too ripe to eat. So when we talk about chemicals and we're looking at a chemical label, for example, we see this hazard diamond, and you see different numbers and different colors, and so every color represents something else. So, for example, if it's blue, it represents hazard, health hazard. The number 3 represents the magnitude of that health hazard. So, in this case, this chemical is extremely dangerous. Okay, the red represents a fire hazard. 4 means it has a flash point below 73 degrees Fahrenheit, which means you have to keep it very cool in a cool room. Reactivity is a 2, so it's violent. It has a violent chemical change that occurs when it reacts. The color white specified, it means it's a specific hazard. It means the W that's crossed out means use no water. Okay, so this chemical would have this hazard label, and it would be very, very dangerous to have in the lab, and that's why all chemicals are labeled in such a way where there is a hazard diamond for all chemicals. Even if the chemical seems to be pretty safe, like sodium chloride, for example, table salt, will still have a hazard diamond associated with it and labeled when it's in the lab. So other properties of matter, you have extensive properties and intensive properties. So an extensive property of matter depends on the amount of matter present. So examples are mass, volume, heat. So for example, the mass of a substance is going to depend on how much of the substance I put on the scale, right? If I tried to weigh myself and only put 1 foot on the scale, it depends on how much matter is present in order for the mass for the scale to give me an accurate mass, right, for the substance or the person. So it depends on how much you put on the scale in order for the value to be what it is. So volume is another example. If I want to measure the volume of a bottle of water, and I wanted to verify that it was 500 milliliters, I would take that water and pour it in a graduated cylinder. And if I didn't pour all of it, that would affect how much volume I have, right? So it depends on, an extensive property depends on how much of the substance I use. An intensive property does not. So if it doesn't depend on the amount of substance of matter that's present. So for example, density. The density of water, for example, is 1 gram per milliliter. And that's going to be true no matter if I use 500 milliliters of water to determine the density of water, or if I use a liter of water to determine the density of water. That number is going to be the same no matter how much I use. And that's because density is an intensive property. Okay. Temperature also is an intensive property. Okay. So it doesn't matter how much of the substance, it's always going to be a constant value. All right, so I said earlier that when we look at the periodic table, we're going to point some things out. So I'm going to point out some things that your textbook is talking about, and then I'm also going to discuss some other things while we're here looking at the periodic table. So obviously, I've already discussed about the different letters. Usually if Y, for example, it's hydrogen, a capital H, and helium is capital H and E. So basically, if the element was discovered, was the first element discovered, for example, hydrogen was discovered before helium. And so what happened was hydrogen got a capital H, and then helium was discovered later. And so differentiate between the two, helium was assigned He. And so the second letter, lowercase letter for helium, is usually going to be whatever that letter happens to be. But if another element